So right now I'm in a parking lot and there's a stop sign right ahead of me. I'm going to accelerate to 20 miles an hour and remain constant at 20 miles an hour. Then I'm going to come to a stop. So there's the stop sign. And I'll be traveling 13 of these sidewalk squares. First, calculate the mass of the car. It weighs 4,001 pounds, but when converting that to kilograms, it's 1,800.45. Next, calculate the speed. It's initially traveling at 20 miles an hour. When converting that to meters per second, it's 9 meters per second. Now calculate initial momentum using P equals mv, and you'll get 16,204. Now calculate change in momentum, and you'll get negative 16,204. Now calculate the distance the car travels. It travels 13 sidewalk squares and each square is 8 feet. So 8 times 13 and you get 104, and convert that to meters and you're going to end up getting 31.2 meters. Now calculate the force. You're going to end up with negative 1,841.4 newtons. This bar chart demonstrates how momentum is conserved. As I start at 20 miles per hour, then I decrease by 20 until I get to 0.
Impulse is equal to change in momentum. It's also equal to force times time and mass times change in velocity. A ping pong ball with a mass of 0.0027 kilograms comes towards the paddle at a speed of 13 meters per second. The paddle hits the ball with a net force of 1,200 newtons, and the ball travels in the opposite direction with a speed of 22 meters per second. What is the change in momentum, and how long are the ball and paddle in contact for?
When pool balls collide, they usually create an elastic collision. For example, after the white ball collides with the red ball, they go in opposite directions. In elastic collisions, the total momentum before the collision is equal to the total momentum after the collision. Since the red ball doesn't move until after the collision, the velocity equals 0, so that part cancels out. We use distance over time to calculate the velocity. Because the red ball moves in a negative direction, it'll have a negative velocity. Before the collision, the white ball moves 0.2 meters in 1 second. After the collision, the white ball moves 0.9 meters in 2 seconds, and the red ball moves negative 0.6 meters in 2.3 seconds. The white ball has a mass of 0.17 kilograms, and the red ball has a mass of 0.16 kilograms. When you calculate the value on both sides, you get 0.034 equals 0.034. Since the value is the same on both sides, that means the system neither lost or gains momentum, so momentum is conserved in this example. On this zip line, the collision between the girl and the front tire is inelastic. As she collides with the tire, some of her momentum is transferred to it. On the left, you can see that the initial momentum of the girl was 364.8 kilograms meters per second, and the initial momentum of the tire was 0. On the right, you can see that the girl's final momentum was 284.8 kilograms meters per second, and the tire's final momentum was 80 kilograms meters per second. In the middle, you'll see that she lost 80 kilograms meters per second when she transferred it to the tire that gained 80 kilograms meters per second. Momentum before the collision equals momentum after the collision. The girl has a mass of 32 kilograms and the zip line is 91.5 meters long, and it takes her 8 seconds to get to the tire. The tire has a mass of 9 kilograms. After the collision, the girl and the tire have a combined mass of 41 kilograms. They then travel 17 meters. How long does it take them? First, you solve for the initial velocity and momentum. Then you divide both sides by 41, solve for x, and then you should get 1.9 seconds. Now we can calculate the net force of the tire on the girl using change in momentum equals force times time. When we plug our momentum and our time in, we get net force equals 192 newtons.